What's up, guys? Thought I'd do this video in two parts because it's so important that we know these in lots of detail. So we're looking at our first practical here. We're looking at titration and standard solution. So we'll do the first video looking at the creation of the standard solution. Then we'll look at the method behind titration, including the sort of table that we draw. And then we'll start looking at the calculations for titration. So sort of three parts. Let's get into it. So we start off by weighing out our sample, all right? So the whole point here is we're creating a standard solution with an exact concentration, something that we're very certain about. So we've got to be very precise in the things that we're doing. So first thing, we're often going to take our balance, and we're often going to use like a weighing boat, right? So we've got a weighing boat. On a balance containing our solid. We're going to measure our weighing boats and our solids onto our balance. And it's important here that we know that our balance has like 2 decimal places reading on it. So it's pretty precise, okay? What we're then going to do is transfer our weighing boats or our solids to a beaker. With around 100 centimetre cubed of water. And once we do that, we're going to re-weigh our weighing boats. So at that point, our weight of solid is going to be very precise. So in your lab books, you should have a table that looks something like this. So you've got boats plus solid, then just the boats after it's been transferred, and then finally you're going to have weight of solid. And you're going to calculate it down here in centimetres cubed. Okay, once we've done that, we're then going to stir our solution with a glass rod. Stir with glass rod until solid dissolves. That's our next step, okay? Bear in mind, it's possible that some of our solid is going to be on our glass rods. It's possible that some's going to be left behind inside our beaker. So here, we're going to pour it into this. So we've got our volumetric flask. And generally speaking, our volumetric flask is going to be 250 centimetres cubed. So we're going to have an exact line here where once we add our liquid and the meniscus is on that line, we'll know we've got exactly 250 centimetres cubed. But we need to make sure that all of our solid is in there as well. So we're going to pour out beaker. And we're going to plus washings. So what we mean by that is we're going to be spraying our beaker, we're going to be rinsing our beaker with our distilled water here. We're also going to be doing the same to our glass rods here, so that every single piece of our solid is inside our standard solution. We're obviously using our funnel for that as well. So we're going to rinse out the funnel as we go through this. Then we're going to fill our volumetric flask, fill with water, and often we're going to wait until we fill it up most of the way. Then we're going to shake or invert. So shake or invert flask. And you'll see when you do that, say if our level of liquid is here, our level of liquid is going to drop slightly once we shake or invert it, okay? And then we're going to refill until our meniscus, the bottom of our meniscus, is touching that line. And it's at that point we've got exactly 250 centimetres cubed. And there we're going to be very secure in the concentration that we've calculated. Couple of things. So sometimes you're asked about how to improve methods here. So think very carefully about the things that we've done to make sure all of our solid has transferred from one thing to another. Make sure we're really thinking about dissolving all of our solids, rinsing out our washings, careful weighing and reweighing of our weighing boats, shaking and inverting here, making sure our meniscus is on the line. One other thing we can do is we can use larger mass of solids to reduce any uncertainty. Because if we've got a 2 decimal place balance as we do here, our uncertainty there is going to be plus or minus 0.005 centimetres cubed. Okay, so in that case, if we have a larger mass, that uncertainty impact is going to be reduced. As always, so we'll cover the titration bit in the next video, and let's answer the questions from the end of last video. So here we had a past paper question. Magnesium also reduces silicon dioxide, and we've got our equation for that here. It's really important that we remember that all of our questions are often linked. So a question could give us an equation in 1A, say, and then 1D ask us something about it. C, give one reason why the products are difficult to separate if magnesium is used to reduce silicon dioxide. Here, bit of common sense. We've got 2 solids produced here, 2 solids. And no simple way of removing them, like none of those is magnetic. That's going to be a bit difficult. But this is the thing I'm most concerned about, minimum mass in grams. So we've got completely reduced 1.2 kilograms of silicon dioxide. So here, where we've got our equation, we've got our silicon dioxide mass, we're being asked about magnesium. So our calculation is always going to be using this triangle, mass Mr. Mole. Let's get that table drawn. So we've got 2 mg and we've got SiO2. Mass Mr. Mole. And now we fill in our information. So we've got 1.2 kilograms. Let's convert that straight away. So we've got 1,200 grams. MR of magnesium, we've just got 24. For silicon dioxide, again, we've got our masses here. So we've got 1 lot of silicon, so 1 lot of 28, plus 2 lots of oxygen, so 2 lots of 16. That gets us to 60. Once we've got there, to work out our moles, mass divided by MR. Not sure why it keeps doing that. And that gets us to 20. Then we're going to go from there to there. So we've got 1 lot of SiO2, 2 lots of magnesium, so I need double the moles. So times by 2. So I've got 40 moles of magnesium. Mass MR times by mole, that gets us to 960 grams. Circular answer, rewrite it where it tells us, and we're good to go. Happy revising. Again, we'll look at the titration method next time.